purpose of this workshop is to provide you with the background that you need to run simulations and perform parameter estimation within Matlab. There are several different files that are needed as either examples or exercises, and there's also the presentations and the handouts. They will, as they're updated or as they're changed, they will be available at the URL that you can see on the screen. The series is set up into 3 different pieces. There's an introduction to Matlab to provide you with the basic information you need in order to use Matlab. After we cover the different components of Matlab that are necessary, the second part is going to focus on how to create simulations of ordinary differential equations forward in time. And then the third part focuses on how to use those simulations to perform parameter estimations within Matlab. So before you get started on any new software application, you're probably going to ask yourself, why do you care about this piece of software, or why are you interested in learning it? And so if you look at the software applications that are out there for modeling and simulation, now I realize that some of these are for population modeling and some of them are for model structure development. But if you look at them on a continuum, generally speaking, on one end of the continuum you have the most flexibility, and that's over here on the left of this continuum. And on the right, as you move from flexibility, as you lose flexibility, you increase the ability of the programs to be used. You increase its ease of use. And so I've kind of placed things where I would consider them to remain relatively on this continuum. Matlab has two different ways of being used. You can use the Matlab graphical user interface, or the GUI, and the Matlab GUI is much easier to use, but it also is very limited in scope and what you can accomplish in the GUI. And this presentation is going to focus more on how to use Matlab in a scripting environment. So this requires a little bit more effort up front, but the end result is that once you get done with learning this, you'll have a set of scripts, and you'll have an ability or a capacity that's going to make you much more efficient and much more, and you'll be able to derive much more utility from that. So that's my selling point for Matlab. I've designed these slides to basically work with all of the different examples, and so in order to distinguish the examples from the actual text within the slide, I've basically put all of the code that you would type directly into Matlab, and I've put all of the little snippets from the files in this font, this red font shown here. And if I'm discussing an example or an exercise, they are actually all located in this matlab_workshop.zip file. And that's what you get when you go to that URL from the previous slide. Within that, there's 2 different directories. There's an examples directory and an exercises directory. Okay, so all of the examples and exercises that I discuss within this slide set will be found within those directories. Lastly, when I'm talking about typing commands directly into Matlab, I'm going to use this 2 greater than symbols. These 2 greater than symbols represent the Matlab command prompt. If you open up Matlab, by default, you're going to see something similar to this. Depending on your operating system, it may look a little different, but basically you have these 4 main windows. The command window is sort of it's the place where you actually interact with Matlab. It's where you type in individual commands, where you assign variables, where you run scripts and execute functions as well. As you create variables within Matlab, these variables are going to appear in the workspace. So the workspace will list all of the current variables that are defined within Matlab, and you can actually graphically click through them to see what their contents are, to kind of verify what you believe. As you type in commands in the command window, MATLAB will keep track of the different commands that you've typed in the command history window. Okay. And part of running any analysis is that you're going to want to be able to save files and execute them. And so MATLAB has a path that it searches through where it finds all of the built-in MATLAB commands. But by default, it'll also look in the current directory. So right here is the current directory, which is in my documents directory. And it's empty, but normally if there's any files present, they'll show up here as well. It's important to note that MATLAB is a case-sensitive language. So what does that mean? That means that if you define a variable within MATLAB, and you have defined the variable in terms of uppercase, then when you use that variable, you have to use the same case whenever you're using it. So capital A is not the same thing as lowercase a. Also, MATLAB has a very good documentation system. So if you want to bring up the documentation in MATLAB, you can just type doc in the command window and hit enter, and it'll bring up the help window. And then you can search through all of the different built-in MATLAB commands here, and you can find information about them. So if you want to use the plot command and you're not familiar with the syntax or the different arguments to that command, you can just type in plot here, hit enter, and it'll go through and search the documentation for the term plot. And the first thing that comes up here is the plot function. It provides you with the graphical alternative. It provides you with the description of the alternative. It tells you the syntax of the plot command. So this is how you would use the plot command within MATLAB. And then there's a description of what these things mean in more detail. This is all in hypertext, so if you don't know what line spec means, or if you don't know what different options you can use for line spec, then you can just click on line spec, and it'll bring up the line spec documentation page. And then you can scroll down and find this information. So if we're discussing a MATLAB command and you want more information about it, this is where you come to find that information. Now, there's two different major categories of variables in MATLAB that I'm just sort of, these are categories that I kind of create. There's basically very simple variables and there's complex variables. In MATLAB, everything is a matrix. So by default, every simple variable is a matrix of some sort. And you can create a variable that has only one value, and that's a matrix, but it has one row and one column. So if I type A equals 1, and I put a semicolon after it and hit enter, you'll see that the variable A has appeared here in the workspace, and we can see what the value of A is. And if I resize this, it has other information about A as well, the min value, the max value. But the min value and the max value are going to be 1 as well, because A only has one dimension. So this is how you assign variables within the command window, and this is also how you assign variables within scripts and functions. So if I type A equals 1 and I leave the semicolon off, what MATLAB will do is it will echo what has been done. So I know that A has been set equal to 1. Now if I want to create a vector, I can create a vector by assigning a variable equal to a list of numbers in brackets. So I can type B equals, open bracket, 1, 2, 3, 4, close bracket, semicolon, enter. So now B is part of the workspace. Instead of having a single value, it has 4 values. It has a minimum value of 1 and a maximum value of 4. Okay. Now B in this case is called a row vector because it has only one row but multiple columns. I can make a column vector by typing C equals 1, 2, 3, 4, and I can put a single quote after this. And the single quote is a transpose operator. So you'll notice that C looks very much like B, except that there is a semicolon after each element within C. So I could actually type C just like that and leave off the transpose operator. So C is equal to 1, semicolon 2, semicolon 3, semicolon 4. And that has the same effect. Now I'm going to type it as I did the first time, but I'm going to remove the semicolon at the very end so that it will display what C is. And I'm going to type it like I did the second time, but I'm going to remove the semicolon, so you can see that C is being assigned the same way, either way. When you're using the Matlab command interface, if you want to bring up previous commands, you can hit the up arrow or the down arrow, and what that does is that scrolls through the command history. One last way, I could also assign C is equal to, and when I open the bracket, I can type in 1, and then I can hit enter. 2, 3, 4, and then I can close the bracket and hit enter. And that's another way to construct a column vector. Okay, it doesn't detect that I've fully entered the command until I close the brackets. So as long as I have the bracket, the left bracket open, it thinks that I'm still entering values into C. So that's how you can create a column vector or a row vector. It's also useful to be able to create arrays or matrices. So you can create multi-dimensional arrays or matrices within Matlab. But for the most part, we're just going to stick with two-dimensional arrays or matrices. So in this case, I can say D is equal to 1, 2, 3, 4. And then I'm going to put a semicolon here. What this means is that I'm going to the next row. So the first row is 1, 2, 3, 4, 5, 6, 7, 8. Then I'm going to close it and hit enter. So now we see that D is an array that has 4 columns and 2 rows. And if we go over here to the workspace, we'll see that D has a lot of information. It shows you the very beginning of it. That is a minimum value of 1 and a maximum value of 8. So that's how you can enter numeric data into Matlab. The last thing that we want to do is we want to talk about text data, because it's important to be able to enter strings of information. So a string is basically a string of text. It's also considered to be a character array. E is equal to, and if I put a single quote here, I can start typing in text. So string of text. Now, until I close this with another single quote, it's just expecting more text to be entered. So I type a single quote there, and you can see that the color changes from sort of an orangish color to a purple color to let you know that you've closed that string. And if I hit enter, we see that E is assigned to the value string of text. Up until now, A through D, we were defining numeric information. You'll notice that E is textual information. This is differentiated because if you look at the little icon here, this AB indicates that we have stored text information in E. Okay. So this is how we create simple variables. So once we've created variables, it's going to be important to be able to access those variables. But it's not always necessary to access the entire variable when we're talking about matrices or arrays. It can be important instead to be able to access just pieces of those variables. So to demonstrate this, I'm going to create an array. I'm going to say that A is going to be a 3x4 array, which means it's going to have 3 rows and 4 columns. So I'm going to make that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's how I created my array. Now, say for example, I want to access a specific element of this array. So in this case, I'm going to want to access this 7 here. In order to access this array, any elements or ranges of elements within an array or a vector, we use this parenthetical notation. So we type the variable that we want to access the element of, open parentheses, and then the row or rows and the column or columns. So this is going to be in row 2, comma, column 3, and then we close parentheses. So if I hit enter, that's going to return the contents of the second row and the third column. it's very important at this point to mention that indexing of arrays and vectors in Matlab begins at 1. This is going to be important because when we start talking about how to write models in C later on, that indexing within C begins at 0. Okay, but within Matlab, within the Matlab command window and within Matlab functions and scripts, array indexing begins at 1. So now, it's not always necessary to pull a single value from an array or a matrix. Sometimes we want to pull multiple values from an array or a matrix. In order to do this, we're going to use the colon operator. So if we look at this A matrix that we created just recently, say we want to pull all of the columns from row 3. So we want to pull the 9, 10, 11, and 12 out of the A. The way we do that is we tell it that we want the third row, but we want to use the colon operator to specify all columns. Okay. Now the colon also can allow you to pull out ranges of information from an array. So say we want to pull out the second and third columns of the first row. Okay. So we want to pull out information from the first row, that's 1. But if we only want to pull out the second or third columns, we can use 2:3. So what we've done here is we've specified a range of values. And actually, the colon operator can be used outside of an array or a matrix when we're trying to pull information out of it. The colon operator can be used to create any list of numbers based on integers. So if I specify any 2 integers, the colon operator will basically create a list of numbers from those. So if I want a list of numbers from, I don't know, 5 to 100, or 5 to 20, I can just type 5:20, and it'll return the list of integers between 5 and 20. The last thing we want to talk about is a special operator or a special term called end. Sometimes when we're manipulating arrays, in this case we know the dimensionality of A, but when we're writing scripts and functions, we're not always going to know the dimensionality of A. But sometimes we'll want to pull all of the values from some point in A all the way to the last column or the last row. To do that, we use the term end. So in this case, in this example, I want to pull all of the information from rows 1 and 2. So I'll type A of 1:2, comma, but I don't want all of the columns. I just want the second column all the way to the end. So I can type 2:end and hit enter. And what that does is that pulls out this upper portion of A. Now, it's important in Matlab to be able to do mathematical operations. And if you've ever had a linear algebra class, you'll know that when you multiply matrices, that it doesn't just multiply elements within the matrix, it performs matrix math. And you can do that in Matlab as well. But most of the time we're not going to be doing a lot of matrix math. We're going to be doing something called array math. Okay? And array math it's also called a vectorized notation within Matlab, means that we're going to be performing mathematical operations on the individual elements of the array. Okay. I'm going to type clear. And what clear does is it clears my workspace. And I'm going to type CLC. And what that does is that's going to clear the command window here. I'm going to define a matrix called A. 1, 2, 3, 4. Now, if I want to multiply the matrix by itself, so say I wanted to square A. So I could do S is equal to A star A. Okay, but this doesn't square the individual elements. This basically takes the matrix A and multiplies it by itself using matrix math. It's not incorrect, but it's not necessarily what we want to do. If we want to do element by element multiplication, so if we want to multiply 1 by itself, 2 by itself, 3 by itself, and 4 by itself, and return that information, we have to use something called the dot operator. So what we have to do is before our multiplication symbol, we have to use this dot, a dot star a. And what that does is that tells MATLAB we're not doing matrix math, we're doing vectorized or array math. Okay? And so what vectorized or array math does is it applies that mathematical operation to each individual element. So this is important because you don't have to do this with every mathematical operation. You only have to do this with mathematical operations that involve multiplication or division or exponentiation. So you don't have to do this if you're adding numbers. So you can add a number to an array, and it will add that number to all of the individual elements of the array. And if that number is actually a vector, and as long as it has the same dimensionality as the array, then it will do element by element addition. So you really only have to do this if you're doing multiplication, division, or exponentiation. In general, just to be safe, I will take any time I'm multiplying things within my script, or any time I'm dividing within my script, or any time I'm using the exponent sign, I'll just put the dot there just in case. And if you do it just in case, you don't have to remember or worry about it. It's also important to note that all of the built-in functions in MATLAB work with vectors. So if we look over here, if A, in this case, is a vector, or if A is a matrix, and I take the sign of A, what that does is that returns a vector of matrix, or matrix, with the same dimensionality as A. And the different components are basically the signs of the different components of A. So let's see an example of this. I can create a vector of linearly spaced elements using the linspace command. So I can say x is equal to linspace 0, 10, 1000. Okay. So what that does is that creates a row vector from 0 to 10 with 1,000 evenly spaced elements. Now, what I can do is I can create y, and I can create the tangent of x. Remember, the tangent of x is just the sine divided by the cosine. That's the sine of x divided by the cosine of x. Now, this is incorrect. You'll see that it just returned a single value. That's because it did matrix math. What we really want is we want to do array math. So if I put a period there, what this will do is it'll calculate the sine of x, it'll calculate the cosine of x, and then each element of sine of x will be divided by the corresponding element in cosine of x. I'm going to put a semicolon after it because there's 1,000 different elements. See? So now we have a vector of x's, and we have a vector of tangents of x's. And we could plot this using the plot command, where we provide the x value and the y value. And you can see the asymptotes here. So now let's look at an example of how to use this array math. If we go to the examples directory, and we go into the vector math directory below that, and if we look at toCompartment.m, we have a little script that will demonstrate how this works. First thing that this does is that we're going to clear all of the variables within the workspace. We're going to close any figures. We're going to define a bunch of times, and then what we want to do is we want to plot the 2 exponential model, right? So if I type toCompartment, it'll run this, and we'll talk a little bit about scripts and functions in a moment. And so basically I've defined my A, my B, my alpha, my beta, and then I've defined C in terms of these. Now you see I have A dot star times the exponent. Exponent, exp is the built-in MATLAB function for calculating the exponent. And we have minus alpha, and then I'm multiplying that by t. I'm using the dot star here. Now this isn't actually necessary because alpha is a scalar value. It has dimension 1 by 1. But just so that I don't have to remember this, I'm going to go ahead and put it. And then these dots mean that you want to continue on to the next line. And we have plus b dot star exp minus beta times t. And then I go through and I do some plotting, and I put some text on the screen so that you can see the two different phases here. And I change the axis to logarithmic as well. Okay, but this is how we do basically vectorized math within Matlab. Now, if you were going to do this in C or Fortran, what you would have to do is you would have to write a for loop to loop through all of the values of t. You'd have to loop through the first value of t, calculate a value of c. The second element of t, calculate a value of c. The third element, and the fourth element, the fifth element, and so on until you got to 1,000. This is just a quick way to write these values, and it becomes very useful later on. So what I'd like to do now is I'd like to take an opportunity to discuss the different plotting commands within Matlab. Now, Matlab has a significant amount of plotting functionality, and this is by no means meant to even be an exhaustive list of the things that you need to know in terms of plotting in Matlab. But I think this is a good basic list that will get you started in terms of performing simple and even fairly complex analyses. The first thing that I want to talk about is the figure command. What the figure command does is it opens up a blank figure, and n is an integer, so it can be 1, 2, 3, 4, 5. And when you type in figure of 1, it'll open up a figure, and it'll open up figure 1. So basically that's an empty palette. There's nothing on it. And then if you type in hold on, what that'll do is that'll allow you to add things sequentially to the figure without overwriting it. If you don't type in hold on and you plot something, and then you plot something else, the second thing you plotted will override the first. Okay? So if you type in figure and then hold on, then you can start adding things to the figure, and you can add them using the plot command. Okay? So you can plot one data series, then the next data series. You can plot your model predictions. You can plot all this information. And then after you plot the information, you're going to want to label it. You can label it using the X label or the Y label commands. And then after you've labeled your figure, you're probably going to want to create a legend. You can use the legend command to do that. The way the legend command works is the first argument to the legend command corresponds to the first series that you've plotted. And you don't have to create a legend for every series. So normally what I do is, if I only want to legend for 2 or 3 of the series, I'll plot those 2 or 3 first, and then I'll plot everything after that, and then I'll use the legend command. The legend command can actually be very intelligent. It will, you can tell it to create the legend wherever there is free space on the figure, or you can specify the location. You can look at the documentation for the legend command to see how this is done. The subplot command allows you to create multi-paned plots. Okay, it's going to create a grid of plots where there are m rows and n columns, and k actually just represents the specific plot or the specific pane or panel that you're interested in. And there's a description of this in a little bit. And then I use the print command within Matlab, and what the print command does is it takes your figure and it writes it to a graphical file. You can create TIFF files, PNG files. I'm actually a big fan of the color EPS files because the quality is much better. And then after you create the color EPS files within Matlab, you can use either Adobe to the full version of Adobe Acrobat to convert it to a PDF, or you can use Photoshop if you have access to that. And there's some free online services on the internet as well. To provide you with a simple example of how to create figures, we can go into the plotting folder, and we can look at plot sample. So what this does is it clears all of the variables that are in the workspace. That's what this first command does. Then after we clear all these variables, close all will close any figures that are currently open. Because if there's a figure open from some analysis before, and you start plotting on top of it, you're basically just going to add on top of whatever was there before. Then we create a default figure called figure 1, and then we use hold on to say that we want to add things to this. And then I create a vector of x's. So you would, during your analysis, you would create whatever it is that you want to plot. And then I use the plot command where you provide the x information, the y information, and then some information about the marker. In this case, I just want it to be red, and by default it'll be a line. And then we want to add the cosine, so we plot x, cosine of x, and this tells us that we want a black line. And then we can label the x-axis and the y-axis, and then what I'm going to do is I'm going to dump it out to a PNG file. I can click on Run here, and you can see the sine of x, you can see the cosine of x, you can see the x label in radians, and the y label as sine or cosine. Now, depending on the purpose of the figures you're generating, this may or may not be adequate. You can look at the handout and you can see that from a presentation perspective, this is very faint. And one of the powerful things about Matlab is that you can generate these scripts that will basically go through and they will generate figures for you automatically. And then if you want to change something, you just make a small change in that script. So if we look at this other file called plot simple bold, it effectively looks very, very similar to the one before it. We're clearing everything, we're closing all the figures, we're opening a figure, we're telling it we want to hold it, we create a vector of x's, we plot x, we plot y. And then what I've done is I've gone through and I've said, okay, I want to change the font size to 35, and I want to change the line width. And what I'm doing here is I'm using the GCA command. What this does is it gets the current axis. The axis is the axis where the most recent thing that was plotted is on. But these only apply to the axis. It doesn't actually apply to the lines within the axis. So what I can do is I can get the children, and I can set the axis children to a line width of 3. The children here are the actual data series that have been plotted. Then I go through and I do the same thing where I label in radians, label the x-axis with radians, I label the y-axis as sine or cosine, and then I dump it to a file again. So this is all that this file adds. This is just formatting information. When I run it, you see it makes everything much bigger and bolder. Now, it looks kind of odd in the figure window, but if we open the actual PNG file that's generated, it looks a lot clearer. And this actually looks a lot better when you want to print it and whenever you want to use it in a presentation. You want thicker lines so people in the audience can see. So the next thing we want to do is we want to talk about the subplot command. And so I have created this file called plotting multipane. And basically what I'm trying to do here is I'm trying to show you how the subplot command relates to the orientation of the axis on the figure. So in this example, we have an array of plots. There are 2 rows and there are 3 columns. Okay? So each subplot command tells us first the number of rows and then the number of columns. And the subplots themselves are created by a number, and that number goes from left to right and then from top to bottom. So if I want to access this subplot, this is the 1, 2, 3, 4, 5, 5th subplot. So then to access this axis, I would use subplot 2, 3, 5. Then once you've issued the subplot command, you can plot anything you want to on that axis, on that little pane. And then you just use the same plotting commands that we used in the previous examples. So before, when I was discussing the different types of data that can be stored, I said that there were, in variables in Matlab, I said there were basically simple variables and what I would consider to be more complex variables. And so the scalar, the array, and the vector, and the string of text are basically very simple things, but normally when we're performing an analysis, we're going to want to be able to store a little bit more complicated information. into into variables, because we're going to want to be able to pass this information from the workspace that we're currently working in into functions and into other scripts. And so there are a couple what I would consider to be complex data types that are going to be useful to us in MATLAB. The first one that I want to talk about, I don't use this a lot, but it's called a cell array. And so basically normal arrays within MATLAB can store one kind of information. So if you have an array that has numbers, it's just numeric information, and you also want to store text, it can't do that. And actually, if you have text data in a normal MATLAB array, the text data all has to be the same length. So if you wanted to store the string fox in an array with the string dogs with an S, then you would have to add a space to fox to make it the same length as dogs. Okay. But what MATLAB does is it creates these things called cell arrays, and cell arrays allow us to store different types of information in matrix form. I think this is very similar to data frames in the R programming language. As an example, say we wanted to store observation data, okay, like we have shown here. So if we wanted to store this observation data in MATLAB, we would want to store not just the numerical information, but we also want to store the textual information as well, time and ops in this case. We can create this as a cell array in MATLAB by typing it in just as we would a regular array, with the exception that each element has to be surrounded by curly braces here. So if we surround each element by curly braces, MATLAB will know that we're creating a cell array as opposed to a regular array, and it will identify that and it will create it. I'm going to create the first few rows of this in MATLAB. So I can type A is equal to open bracket, because A is going to be a matrix or an array, but the elements are not going to be numeric. They're going to be a combination of numeric and text information. So that creates the first row. And then if I want to create the second row, I just type it in as I would like a normal numeric value, but I surround it with little curly braces. And then I can type in the third row. And if I hit enter, it'll create this cell array, time and observation. Notice those two are strings, but the rest are given in these little brackets. And if we look at the variable A that was created in the workspace, we'll see that the little icon associated with it has those curly braces as well, and that indicates that it is a cell array. I use cell arrays a little bit, but for me, a far more useful data type are the data structures in MATLAB. And so what data structures allow you to do is they allow you to group information in a hierarchy of sorts. And so basically a data structure has different fields, and these fields are joined to the data structure using the dot operator. Okay, so using a period. And so I think this is best understood if we look at an example. And so what I did is I took the information from the previous slide and I kind of arranged it how I would arrange it in a data structure. Okay, but I've added some other information as well. So the first thing we notice is that we created one variable, in this case called subject. Okay, so subject has a field. That's what this dot does, is it creates a field called description. Okay, description contains textual information. So I said that that's going to be equal to, and in this case, a string of text. And so evidently this information is about an experiment where we're provided with the plasma concentration of the drug, and it looks like that it was dosed at 40 micrograms subcutaneously. Okay. Next we have a field called times. Time has another field called values. Okay, and this is just numeric information here. So these are the values associated with time. And I also like to include the units. So I have time here, but it has another field called units, and I said that these units are in hours. And then I have Then subject has another field called obs. This is where we store our observation. And just like time, it has a field called values and a field called units. The values are the same values from the previous slide, and the units evidently here are nanograms per mil. So subject.description is just a string of text. But time and observation, those fields are also data structures. And those fields have fields below them. So you can create sort of a hierarchy to represent the information that's stored within Matlab. I think this is very useful because basically you can create all of your data and you can stick it in one variable, and then you can use that variable to pass it from your workspace that you're working in down into the subfunctions that you're going to have to create. If you've been kind of typing along, or if you've been playing with Matlab at all, you may notice that you typed a series of commands, and then at some point you realized, wait, I made a mistake. And you can use the up arrow to kind of go back and get to that command, and you can fix your mistake. But then you have to go back and reissue all of the subsequent commands that depend on that command, right? So this can become kind of tedious, and you may make more mistakes. So what you can do is, instead of typing all of your commands in the command window, you can create something called a script. Okay, so basically a Matlab script, they're also called M files, is a text file, like a normal .txt file, except it has a .m extension. So when Matlab sees it, it knows it's either a script or it's something special. And basically it's a text file that contains the commands that you would type into Matlab just as though you were typing them into the command window. And you can also comment scripts by using the %sign. So anything following the %sign within a Matlab script is a comment. Once you've saved your file, you can execute it in two different ways. So if we go back to our plot simple bold command, okay, this, if we look at it, is simply an M file, and it's a script. So it contains a bunch of commands associated with plotting. Now, I can execute this by clicking on this little icon here, and it might be a little bit different in Windows, but effectively there's an icon up here. What it will do is it will save any changes that you've made to it and then run the script for you. So if I click on that, it saves the changes and it runs the script. Okay. Alternatively, I don't have to edit it. I can just type in the name of the script without the .m extension within the command window, and as long as that script is in my current directory, it'll execute it. It's important that it has to be in the current directory. So if I type plot simple bold and hit enter, it's going to execute that script as well. So let's look at an example. If we go to scripts and functions, there's a file called script_example.m. Okay. What this does is this uses the built-in random number generator in Matlab to generate a random value. This is a normally distributed random number. So rand in, it's going to generate 1,000 of those. And basically it's going to generate 1,000 rows in one column. And then I go through and I multiply that by 100. So that gives me my x data. And I'm calculating the median value, I'm calculating the mean value, and then I'm printing a histogram. And then the stuff that follows here is I'm labeling things, and I'm changing the font sizes to make them more useful in terms of creating a file that I can put in a presentation, and then I'm just dumping it into a file like before. Okay, so this script will go through and create this histogram for me. So I can change into the scripts and functions directory, and I can type in script example, hit enter, and it's generated my normal distribution. This is going to look a little different because it's generating them randomly each time with my median and my mean. Now what you're going to notice is when I ran that, it created all of these variables within the workspace. I may or may not want these variables, but keep in mind this is a very, very simple script. It's very simple, and that it does something very specific. Normally when you're performing an analysis, the scripts are going to be a little bit more complicated and a little bit more complex. And what's going to happen, or at least what happens to me, is I tend to create lots of different variables within the workspace. Also, if I want to perform a task repetitively, if you want to do this within a script, you basically have to copy and paste the code over and over again. So you end up creating pieces of code that have been copied and pasted, and if you want to modify those, you have to go and modify each copied and pasted component. Scripts are useful in automating things, but they tend to create a lot of clutter, and they also tend to get cluttered themselves because you're copying and pasting things that you want to do recursively, or you want to do successively. What Matlab does is, along with scripts, they also give you the option to make functions. Now, the functions are things that you're actually familiar with. If you've used adapt at all, you know that when you edit the Fortran file within adapt, it has different subroutines. A function or a subroutine, these are all effectively the same. Functions are a way to encapsulate a series of commands. And when you have a function, the only thing that function sees from the outside are the things given as the inputs. So it doesn't really matter what you've defined within your workspace. The function itself cannot see the contents of your workspace. The function itself can only see the inputs, or they're sometimes referred to as the arguments of the function. And the only thing that you can see internally within the function are the outputs that the function provides. Now, you've used functions before, you just don't, you possibly might not realize it. For example, the sine function is a function. You don't know, and I don't really know, how MATLAB calculates the sine of x. Is it using some sort of Taylor series expansion? I have no idea how MATLAB is calculating the sine of x. All I know is that if I give it an x value, or if I give it a vector of x values, it's going to return a y value or a vector of y values corresponding to the sine of those x values. So you don't really care how the sine works, you just know that it works. Okay, so in this case, sine is the function, x is the argument or the input, and y is the output of the function. Basically, you can create a function in MATLAB by changing one thing on a script. So the way that MATLAB knows a function is a function, or a user-created function, is that it's an M file, and the very first line of that M file says function, and then in brackets, the different outputs of that function is equal to the name of the function, and then in parentheses, the different inputs that function is expecting. Okay? So it's important. You shouldn't put anything before this function declaration. You should just place this function declaration at the very top of your M file. It's also very important to know that the only thing this function, I'm gonna reiterate this because it's very important, the only thing this function can see from the outside are the variables passed to it as inputs. Okay? And the names used inside the function have no correlation to the names used outside the function. So what's going to happen is, in this case, function name will be given possibly two arguments. The first argument used in your workspace could be Bob, and the second argument could be Sam. When you call this function, Bob is, whatever the value is in Bob, it's going to be placed in N1. And whatever the value is in Sam will be placed in N2. This function has to create the variables out1 and out2 somewhere within it. And then you can create as many intermediate variables as you want to make your analysis simple for you to understand. But you have to create out1 and out2 so that this function can return those variables to the workspace. One other thing about functions is that they have a specialized commenting system. Okay? So this function would be called function_name.m, and it would be called from the command window by just typing function_name and then leaving off the .m and in parentheses your input arguments. Okay. The block of comments immediately following the function declaration. Okay. So right here we have the line numbers. This is line number 1 in function_name.m. This is line number 2, line number 3, 4, all the way up to 7. The block of comments immediately following the function declaration will basically provide the help for that function. So if I create function_name.m and I create it with these contents, and then I save it to a .m file, and then from MATLAB, from the MATLAB command window, if I type help function_name and hit enter, it will return the contents of this block of comments. And this will explain how the function is called, what the format of the inputs are, what the format of the outputs are, and any other considerations the user needs to use or that the user needs to take when evaluating this function. Okay, so I have an example in the scripts and functions directory called function_example.m. If we look at this function takes 2 inputs and it returns 3 outputs, right? So I'm going to clear everything in the Matlab command window, and I want to call this function, so I need to define some inputs in order to call this function. I'm going to define an input called T1. I'm going to give that a value of 10, and T2, and I'm going to give that a value of 2. Now I'm going to call this function, and I'm going to store the contents that are being returned in this by this function in the variables Q1, Q2, and Q3. So type Q1. Remember, these are in brackets. Q2 and Q3 are equal to function underscore example T1, T2. Okay, now let's look at this. Things that you should notice. In this case, T1 has a value of 10. This is the first input argument to function example. Okay. T2 has a value of 2. It is the second input argument to function example. Now function example is going to return Q1, Q2, and Q3. That gives us a value of 20, 5, and 100 after I run this function example. Now notice that in the function itself, the inputs are A and B. So T1 corresponds to the first input, which is A, and T2 corresponds to the second input, which is B. Okay. In the function example, the first thing returned is M, the second thing returned is D, and the third thing returned is P. M is basically the multiplication of the 2 inputs, P is the exponent of the 2 inputs, and D is the 2 inputs divided by each other. Okay? Now, Q1 is going to hold the contents of M. Q2 is going to hold the contents of D. And Q3 is going to hold the contents of P. Okay. It's very important to realize that there is absolutely no correspondence between the names that are used for the function inputs and the function outputs within the function itself and the names that you use when you call them from within Matlab. Okay? They are completely independent. There's just a mapping of the order. The first thing sent into it corresponds to the first input. The second thing sent into it corresponds to the second input. The first thing returned corresponds to the first output. The second thing returned corresponds to the second input. And the third thing returned here
basically
corresponds to the third output. What the situation that you have is you're performing some sort of analysis within Matlab, and maybe you want to turn your computer off. Maybe you want to put this aside and come back to it in a week. For whatever reason, you want to stop what you're doing, but you don't want to lose all the information that you have. And so what Matlab does is if you have a bunch of information within your workspace, then you can just save this information to a file. Okay, so Matlab has this save command. So say I'm creating some variables. I have v1, that's going to be equal to linspace of 0,10, and v2 is going to be equal to v1 plus v1 squared. Notice I use the dot operator. And v3 is the sine of v1. Okay, so you'll notice that what I have done is I've created these 3 variables in the workspace called v1, v2, and v3. Now what I'm going to do is I'm going to change into this little temporary directory here. So if I want to save information, but say I don't want to save all the information, well, by default I can save all the information. If I type save and then all.mat, what that's going to do is that's going to create this file called all.mat, and it will have all of the variables that have been defined. So if I type clear, you'll see that I've cleared all the variables. The workspace now is empty, so there's no variables currently defined. And now what I can do is I can type load all.mat, and that will load all of the variables. So now I've basically recovered all of those variables. Now, if I really don't want to load all of the variables, say I'm performing an analysis and I just want to load two of the variables, say v1 and v2, I can type load all.mat v1 v2. So now I've only loaded v1 and v2. Alternatively, if I say I just want to save a couple of the variables from the workspace, I can type save. It's basically, let's go and load all of the variables. Okay. So I just loaded all of these variables. Now I can type save sum.mat v1 v3. Now if I type clear and I load sum.mat, I'll load all the variables that are currently stored in sum.mat, and that's going to give me v1 and v3. So we can use these save and load commands to load some of the variables, or all of the variables that are saved, or to save some of the variables, or save all of the variables, depending on what we're interested in. If we're performing an analysis, say we're performing a parameter estimation, at the end of the parameter estimation, I typically save my parameters, and I save my solution statistics, CV percents, and confidence intervals, and I also save any information that was used to generate those. So if I'm performing a kind of a complex analysis, and I have a data structure that kind of describes how that analysis was performed, I'll save that as well. And this way I can load it later on and maybe generate figures or do some sort of other analysis associated with it. So that's pretty much all the pieces of Matlab that are required in order to perform simulation and parameter estimation, at least all of the basic components. And so I'm going to leave you with an exercise, and you can basically, this is an exercise that kind of sums everything that we've done up to this point. What I want you to do is to first write a function. Okay, so within Matlab you want to write a function to calculate a polynomial, y, as a function of x for any given set of coefficients. Okay, and this is a third order polynomial, so you need to have, you're going to expect, your function should expect that you're going to have 4 different coefficients and maybe a vector of x's. There's no one way to find this solution. So after you've written your function, you need to write a script, and you're going to have that script calculate the values of y from x equals -10 all the way to +10. And then you're going to do it for 2 different sets of coefficients. And then after your script calls your function and evaluates it, then what you want to do is you want to plot these values on the same figure. So you can pause the presentation here and work on this. Okay, so the solution here is found in the function _exercise directory, and the first component is this calculate _polynomial.m. So this addresses the first bullet point. We want to create a function to calculate my polynomial. Now it's important to realize that there are different possible ways to answer this problem. Some ways are more efficient than others. Some ways may make more sense than others. So when you're writing programs or when you're writing functions or scripts, try to make sure that when you come back, you can actually understand what you're doing in the future. So the first line here is my function declaration, and it's going to return something called y, and the name of the function is calculate _polynomial, and it takes as its input x and p. Okay. Now down here, the first thing I do is I take my p's and I map them. So I take p1 and I map that to a3, p2 and I map that to a2, p3 gets mapped to a1, and p4 gets mapped to a0. This is more out of my own convenience. And then I go through and I just calculate y. So y is going to be equal to a3 dot star x dot hat 3. So this is basically the cubic component, the square component, the first order component, and the 0th order component. And that's it. This is my function. So next I created a script to call that function. I called this script plot underscore polynomial.m. You'll notice that the first line here is clear. It's not function, so this is a script. Okay. Then I need to plot it from -10 to 10, so I create a bunch of x values using the linspace command. Now, in the first y that we need to calculate, the coefficients in this case are -1, 3, -1, and 0. There is no coefficient of x to the 0, right? Then I use my calculate polynomial function that I created in the previous slide. I send in the x values, and I send in the coefficients. This is going to return a y value that I'm storing in y1. Okay. Then I create a different set of coefficients, okay, and I call calculate polynomial. Now the x values are the same x values as before, so there's no reason to redefine them. But my coefficients changed. It's 1x cubed, 2x squared, 0x, plus 1. So I call calculate polynomial, and I store this polynomial in y2. Then I close all of my figures. I open figure 1, and I turn hold on. And then I plot everything in one go. I plot the x values, y1. This is going to give me a solid line, which by default will be, I believe, black. And this plots the x values, y2, and this will give me a red dashed line. I use boulder to make it thicker, and I label my axes. I stick a legend on there. I turn the legend box off, and then I just dump it to a file. Okay. Oh, I believe it's blue. The default color is blue. So here we have y1 and y2 from -10 to +10. So there's many different ways to do this and different ways to accomplish this, and there's not necessarily a right way or a wrong way. But the thing that Matlab gives you is it gives you the creative freedom to do things however you see fit and in whatever way seems to work for you.